Welcome back. In this section, we are going to now extend our understanding of statistical mechanics to a deeper level. And so, bear with me. It's going to take a bit of your thinking and attention. So, we are going to start with some of the ideas that we started with Boltzmann distribution, but now we are going to focus on partition function and how it is able to allow us to create lot more advanced understanding of the statistical system. So, if you look at your slide now, we start with the probability distribution, and if I look at I number of particles, and it could be any number of particles, if I sum them up, all probability has to go to unity, because there is a partitioning of the probability, and that is where we go into with average energy E, which is time average, and a fixed number or ensemble average in this case when we are looking at the statistical mechanics, with a fixed number of particles in thermal equilibrium at temperature T. The constraint on the total occupancy and assembly energy R, that there is a Pi is the probability of occupancy of that microstate multiplied by its energy EI, and that becomes a what we call is the internal energy, as we saw earlier. Now, if we maximize entropy S, and we understand earlier that entropy is related with Kb, Pi if it was I atoms, logarithm of all the occupancy of the probability is Pi. So, now if I look at under Pi and J, so if you look at this particular function, you can see that it is almost similar to master equation, where you have the first term, which is entropy, the second term is also looking at some of the work, and the third term is also change in internal energy due to some of the changes in the average energy over the changes in the energy because of the interaction of the atoms and molecules. So, if I take any set of atoms which are in a particular temperature level, and then I can formulate their Pi for that particular state, let us say temperature 20 degrees Kelvin, as compared to the entire ensemble over I, then that is where we come up with this ratio, as we said earlier. That ratio gives me a partial probability function, and that is now represented by the overall average of the entire ensemble, which is given by a partition function Z. This Z function is the partition function. So, if I know the overall distribution of probability over all ensemble particles of number n, then that Z becomes an important quantity called the partition function. And if I have to just look at a gas at temperature T, if I want to find out the partial probability of finding the gas molecules at that temperature T, and those are I number of particles, then all I have to do exponential EI of KBT at temperature T, and I will know the probability distribution. And I think that is where now we look at the thermodynamic potentials, and then use now the partition function in order to calculate our thermodynamic potential, like du, change in the internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. So, if you look at on your slide, now I look at each state function has corresponding exact differential, and these are the exact differential from which we call master equation. So, these are the four master equation which are connecting with the thermodynamic potential with the state variables. And the state variable are Ts and Pv, or Ts and Vp again in terms of volume being constant and pressure being changing, and in dF it is S constant, entropy and the pressure constant, and G, which is the Gibbs free energy, S constant and volume constant. If you look at, they are always in the form of intensive quantity multiplied by another extensive quantity. So, these are the conjugate pairs. Master equation for a state function can be obtained from the first law using the Legendre transformation. So, now let us talk about the partition function. Partition function is the one which will be dividing to any other situation of the microstate. So, you look at the entire microstate, and then you sum all of them up over n number of microstates, that is when you get the partition function. So, if you look at the denominator in the expression Pi is called the partition function, is usually denoted by Z, and Z is equal to summation over I, number of microstates, exponential of minus EI, energy of each microstate over kBt. And if you look at partition function is the dimensionless normalizing sum of Boltzmann factors over all microstates. So, when you divide that, then everything gets dimensionless and it gets normalized, because as you know, summation of all probabilities should lead to unity. It is extremely important because it relates to the microscopic thermodynamic variable, which we cannot measure, to the macroscopic function of the state, which we can measure. So, this is where microstates and macrostate gets connected through the partition function, and it is a complete thermodynamic description of the system, because we are looking at all n such microstate which constitute the macroscopic nature of the thermodynamic system. And that is why we can now connect it with the Helmholtz free energy as well as Gibbs free energy, which we understood earlier, which are the potential, which is the energy contained in the system, which will lead to certain phase transitions. So, if you look at thermodynamic functions on your slide, and we talk about F, which is the Helmholtz free energy function, and we can use now partition function to calculate that. So, if you want to create F k minus kBt ln logarithm of Z function, which is the partition function. If you want to find, as we said, the internal energy, and if you know dz over d beta, which is the volumetric changes in the system over 1 over Z, then you can find the entire internal energy. Also, you can find entropy from that, and entropy in terms of the partition function is Kb, which is the Boltzmann constant, logarithm of Z, the partition function, plus E over T, which tells you how much energy per temperature is provided to the system. Use the relevant Maxwell's relationship, which are essentially transforms from the Legendre transformation, to obtain other thermodynamic functions. So, if we know S, if we know T, if we know V, now we can formulate other thermodynamic potentials and the functions that are of interest to us. If you look at the diffusive equilibrium, various number of particles via the grand partition function. So, we can also apply the partition function in terms of grand canonical ensemble, where it becomes grand partition function. So, if you look at, that is where we now go back with the what we call as partition function, which is connecting us with the thermodynamic macroscopic measurable quantity. And so, that is where we now apply the ergodic hypothesis, because now if we have large enough ensemble average, if you have large number of n number of states, and we saw in previous calculation that 25 particles were not enough to reach the thermodynamic limit. There was a lot of fluctuation, the system was not getting into equilibrium. So, in that case, a phase point for any isolated system has to pass successively through every point compatible with the energy of the system before finally returning it to original position. So, what we are saying is that the reason we need ergodicity, because in that phase space, pressure, temperature, volume, each microstate, the atom has to sample all energy surface in order to get the right statistics for us, and that is the thermodynamic limit that we are talking. And that is when we can then connect the ensemble properties like volume, pressure, total energy, temperature, thermodynamic potential with different ensemble, and then create the statistical ensemble of large samples, so that we can then use, if you look at in this at the bottom of the right hand side of your slide, you are now looking at the use of partition function. So, if you look at EVN ensemble, now we can find out the total energy simply by adding all the microstates over the volume. And canonical, where T is constant, TVN, you can look at that. In this case, probability of state can be obtained from partition function over beta E. We can also look at that isothermal, and similarly grand canonical. So, the partition function is very, very good for us, and we can use NVE ensemble and understand that we can start with as we did in the 25 particle system. start with now a NVE ensemble with molecular dynamics. We essentially calculate forces on each particle from the derivation of the force field, then integrate that on all microstates using a finite difference scheme with some time step delta t. And when we do that, we then calculate the forces on atoms and repeated process to generate thermodynamic trajectory in the NVE ensemble, which essentially then takes us to what is we call statistical temperature. And we understood that that's come from the Boltzmann distribution. So, what we are going to do now understand the statistical temperature, and we will get into some of the higher level kinematics of the ensembles. So, we are starting with NVE, which is the ensemble we looked at with 25 particles, which was the microcanonical. And now, if we can understand how to create the temperature as constant using Nose Hoover thermostat, then we can move to canonical ensemble. Thank you.